Hello and welcome back. On this video, we are going to define the notion of the product space and the product metric. Suppose we are given two metric spaces with its own metric functions. Now we want to define the product space, which is a set, that's just the set of tuples, where M is in the first space and N is in the second space. So that's our set. Now we want to define a distance function for 2 points, say P1 equals x1, y1, and P2 equals x2, y2. Then we want to define the notion of a distance between P1 and P2 using the two distance functions that are given to us, for the first point being in M and the second point being in N. There are a few ways we can do this, and it's going to turn out that it doesn't matter which one we choose. I'll just give you some examples. So one way to define the distance function would be as follows. I'll just call it d max of P1 and P2. That would be the maximum of the distance between the first entries. Because it's in M, we can compare the first two entries. And the distance between y's. So that will be the maximum distance. Or we can maybe define something like a Euclidean style. We call this d Euclid, P1, P2. I'll just call this as the square root. Just like the Pythagoras' theorem. Let's say dm of x1, x2. We'll just take the first difference between the distance between x1 and x2, we square it. Take the second one, we square that, and then take the square root, like Pythagoras' style. Or we can just take something like a taxicab, and I will tell you where the names come from in a second. Taxicab of say P1 and P2, it will simply be the sum of the two distances. So here are three candidates for defining the product metric, and you can come up with your own idea. And a lot of these, like these three, turn out to be the same. The same in what sense? Same in the sense of homeomorphism. I'm assuming you've watched my video on homeomorphisms and are coffee cup and donut homeomorphic. So what we're going to do is just observe. Before we prove that these three are the same, I'll just show you like what happens if our M and N are R with our usual distance function. Then R cross R would be R2. Right. So if we use the first metric, the distance between these 2 points, it will be the maximum of the distance in the x components. So if we call that point P1 and that point P2, so the maximum distance, if you want to use the maximum metric, we would just be using this distance and say that's the distance between P1 and P2. If you want to use the Euclidean distance, then that will be the distance given by Pythagoras' theorem. We'll just be saying this distance. Or if we are using the taxicab distance, then that's probably how the taxi goes straight to the right and then down, just using sum of this distance plus that distance. So that's where the names come from. Now the question is, in what sense are these three metrics the same? I want you to notice something. So if we take 2 points, P1 and P2, the maximum distance between P1 and P2 is the maximum between x1, x2, and y1, y2, right? Now this thing is less than or equal to, I will just say, the Euclidean distance between P1 and P2. And why is this the case? I am not going to prove it in terms of symbols, because I think it's easy to put in the symbol if I give you the intuition. So here it is. So call this point P1 and call this point P2. So the maximum distance is the maximum of these two lengths, right? And Euclidean distance is this length. What you do know is that this thing, the Euclidean metric, the Euclidean distance, forms the hypotenuse of a right triangle. And the maximum distance is just the bigger one of these two. And since hypotenuse in a right triangle is longer than the side lengths, so this inequality is true. And you will see that given any 2 points P1 and P2, the Euclidean distance will be less than or equal to the taxicab distance. And then P2. And how do you prove this? Well, the way you prove this is using Cauchy-Schwarz inequality. Maybe there are other ways. Anyway, and you will also see that taxicab distance between any 2 points is less than or equal to 2 times the maximum distance, P1 and P2. So what this means is that you can show, just based on just this simple observation, what you can show is that given any 2 metric space, say M cross N, I'll just use these two for now, comma D max and M cross N, comma D Euclid are homeomorphic to each other. And when we say we care about spaces, when we say things are the same, we need to define what it means for the things to be same. And whenever we do topology or metric spaces, we care up to homeomorphism. So that means any 2 spaces that are homeomorphic to each other are the same. Okay, I claim these two are homeomorphic, so I need to find a bijective function which is continuous, whose inverse is also continuous. The function I define is the identity function. So that means x comma y goes to x comma y. A comma b goes to a comma b. Okay, now I need to prove that this function is continuous. How do I prove this function is continuous? Let's use the epsilon delta definition. So let epsilon greater than 0 be arbitrary. And I need to find a delta such that the d max of, say, x comma y comma a comma b less than delta implies d Euclid of x comma y and a comma b is less than epsilon. Now epsilon is given, epsilon is fixed, and you need to be able to find a given epsilon, you should be able to find delta. So can you think of a delta? If you choose delta equals epsilon over 2, so what happens? If the distance between x, y, and ab is less than epsilon over 2, you know that d delta, d Euclid, will be less than or equal to 2 times the maximum distance. That'll be 2 times delta equals, that'll be less than 2 times delta, which is equal to epsilon. Okay, how about the inverse function? The one that goes from d Euclid to d maximum. In that case, you just have to choose delta equals epsilon. And you will see that the inverse function is also continuous. So since this function, identity function, is a bijective function, it is a continuous function and its inverse is continuous. What it shows is that the first metric space is homeomorphic to the second metric space. Yes, as such, these two are the same, but we saw in the case of real numbers, the standard metric is not homeomorphic to reals with the discrete metric. But here, these are homeomorphic to each other. You can play the similar games using these inequalities to show that any 2, you can choose product metric with any of these metric spaces, and they will all turn out to be homeomorphic. You can give it a go yourself. and I look forward to seeing you in a future video. Bye.